Hi guys, this is chapter 19. Sorry I wasn't there at school on Wednesday. The cough that you guys may have heard me hacking in class got worse, and I'm genuinely sick. But show must go on. We've got star testing in a couple weeks, and so we need to get through some stuff. So first of all, we're starting with acids and bases. Please be sure to say the word acids correctly, because otherwise the sound, well, anyways. So, starting with properties of acids, we're going to identify the properties of acids and the bases. Acids are aqueous solutions, with most having a higher hydrogen concentration than hydroxide concentration. They are sour if they're tasted. They produce hydrogen in reaction with metals. They look like water, and they are electrolytic solutions. Now, electrolytic, in particular, that's not what I want. Electrolytic means that they are electrolytes and they can conduct electricity through the solution itself. You may have heard of electrolytes. That's the whole Gatorade idea. Yes, Gatorade has some components that would originally have come from acids. Weakly acidic solutions feel like water on the skin, except when there's an open cut. In other words, it stings. So if you've ever had a canker sore or like chapped lips, and you taste an orange or you taste a lemon, and it hurts like a, well, yes, it hurts a lot. That's why the acid in the wound really hurts. And they are neutralized by bases to produce a salt and water. So what we're getting there is an acid plus a base makes a salt and water. Okay, so whenever you mix an acid and a base, they make salt and water. Okay, so some common acids that we find is hydrochloric acid, HCl, also known as stomach acid or muriatic acid, or pool acid. This is kind of acid that you put into your swimming pool if you ever mix the chemicals in your own pool. H2SO4 is called sulfuric acid. HNO3 is nitric acid. That was on your review sheet, I remember, so that's the name of it. H3PO4 is phosphoric acid. And C2H3O2 is acetic acid, also known as vinegar, and this is also known as an organic. This is an organic acid that it's made from this guy right here, the C2H3O2, which is an organic group. It's acetate, that's polyatomic ion. Okay. The properties of bases, they are also aqueous solutions. Most of them having higher higher concentration of hydroxide than hydrogen. Bases are bitter if they're tasted. They look like water, and they are electrolytic solutions. I want to make sure that we get this. This is called, right here, this OH is called a this is called hydroxide. The hydroxide ion is this guy right here, this OH minus. This is the telltale sign for bases. Then when you see the OH at the end of a compound, that is the polyatomic ion, it is the anion, the negative ion of the compound, you should recognize that that's a base. So they're going to ask you which of the following is a base. Look for that OH at the end, and that should be the big clue. Okay, basic solutions feel smooth and slippery to the touch, except in the eyes where it also stings. Do not get this stuff in your eyes. This is like Drano or soap. Soap and Drano are both bases. That's why they are slippery. Banana peels, however, are slippery for other reasons. So things can be slippery and not be bases. However, if you are wondering if something is an acid or a base, one of the characteristics is, well, it's slippery. Bases are also caustic. They dissolve tissues. This is why sodium hydroxide is such an effective drain cleaner. You throw it in your drain, that's the Drano. You throw it into your drain, and it dissolves the hair and the gook, the organic gook that is in the drain that's keeping it clogged. Okay, one of the ways that we can tell the difference between an acid and base is we use an indicator. An indicator is a substance that changes color at different concentrations of hydrogen. So, for example, litmus is red in acid and blue in bases. Okay, and I have a mnemonic here, and I'm going to try and draw it, and it's kind of hard to do without my... Okay, so this is going to be acids are red and bases are blue. Okay, so that's for litmus paper. Acids are red, bases are blue. No, it is not the beginning of a poem. Acids turn litmus paper red, bases turn litmus paper blue. Phenolphthalein is another one. That pH is sort of silent. It's not, but we in America, we say it without the pH. So it's phenolphthalein, and that's a FTH sound right there, and that's just kind of goofy. Is colorless in acid and in neutral solutions, but it turns pink when it becomes basic. Okay, universal indicator has a rainbow of colors. Okay, it's red when the solution is very acidic to dark blue when it is very basic, which is okay because it is consistent with litmus, acid being red and bases turning blue. Okay, so here's an example of some of the colors and some of the other indicators that are out there. The primary ones that you guys are going to see are these guys. You're going to see phenolphthalein, and you'll see, you'll see methyl red when you move on. But the combination of these, let's erase that. The combination of these will get used as a universal indicator. So the universal indicator gets sort of conglomerate of all of these things because they don't interfere with each other. Okay, but phenolphthalein, see how it just starts to turn pink as it gets acidic, as it gets basic. This is the basic side. And these are all examples of the acid-base indicators. So, let's clean some of this up. Okay, so then we get to neutralization reactions. The neutralization reactions occur when a reaction when an acid is reacted with a base of an equivalent concentration. The products do not retain the properties of an acid and a base. They make salt and water, and they cancel each other. Because they cancel each other, acid and base can pretty much be considered opposites to each other because they eliminate each other's properties. Okay, so that's the end of part 1, and we'll do one part for each page that we have in the notes. So we'll stop there, and to continue, check out part 2.